If you've been doing all your problems, you're probably getting pretty tired of writing C's and H's for all the carbons and the hydrogens. And so what we're going to do now is look at a shorthand where we can draw molecules without having to draw all the carbons and hydrogens in. This is called organic shorthand. Condensed formulas take a long time to write for all but the smallest molecules. What we can do with something called organic shorthand is draw a very large molecule quickly. In our shorthand, what we're only doing is giving the carbon backbone and any functional groups that might be on there, any heteroatoms that might be on there, and assume that the person who is looking at this shorthand understands how many hydrogens are on each of the carbons and what's the remaining bonding in the molecule that's not written. What's good about organic shorthand is it gives a better idea of bond angles than the condensed formulas do. And so when we draw with organic shorthand, sometimes we have a real great idea of what kind of three-dimensional structure we might have for that molecule. And it helps us to understand why reactions occur a certain way.
The shorthand actually uses a line to represent a bond between two carbon atoms. If I draw two lines, that implies three carbon atoms. This first structure down here, it has three carbons in it. It's called propane. If I draw a line and then another line at an angle to it, this is representing the three carbons. The corner between the two lines is the carbon in the middle, and the two ends of each line segment is the two end carbons. If we go down even farther to the bottom structure with 5 carbons, you can see there's 4 carbons in a row, which is written by the 3 line segments that are attached in a down-up-down configuration, and then the carbon that is hanging down on the structure on the left is written as a little line segment that connects at the middle of the 2 top line segments. It's very easy for us to draw molecules this way, and then we know that there are carbons at the end of each line segment. We can figure out how many hydrogens are on each carbon by just knowing how many carbons are attached to the one carbon we're considering. For instance, in the top molecule, an N carbon is attached to only one other carbon, so it must have 3 hydrogens on it. Whereas the carbon at the top of the 2 line segments coming together has 2 carbons attached to it, so it must have 2 hydrogens attached to it. Likewise, if we go down to the bottom structure, the carbon that is at the center of 3 line segments coming together has 3 carbons attached to it, so there's only 1 hydrogen on that carbon in the middle. We can also show double bonds with our shorthand structure. If you look on the left at the top structure, you can see it's a carbon with a single bond to a carbon, and then a double bond to a carbon, and then a single bond to a carbon. And we can show that with our shorthand as a line segment, then a double bond, and then a line segment. And at the end of each line segment, you can see there would be a carbon, and by knowing how many carbons are attached to each carbon, we can then figure out how many hydrogens there must be. If I look at the carbon on the left in the double bond, it has 1 carbon attached plus another carbon attached with a double bond. That gives it 3 bonds, so 1 hydrogen must be attached. The carbon on the left in the double bond has 1 double bond and 1 single bond, so there must be 1 hydrogen attached to it also. The carbons that are at the end of the line segment have only 1 carbon attached to them, So each of those must have three hydrogens attached to it. We also show heteroatoms in our shorthand structures. If you look at the bottom, there are 4 carbons in a row in a chain, and we can see that we can have a line there that goes a line segment 1, 2, then another line segment that would be 2 to 3, and then another line segment would be 3 to 4. To the second carbon, there's another methyl group attached, another carbon attached, so it's shown as a line segment going off. And then to the third carbon, there's another carbon, there is an oxygen attached, and so it is shown as a line going up and ending on the oxygen. There is no carbon at the end of that line segment that is going to the oxygen. It is showing that the oxygen is bound to that carbon. Sometimes we'll use symbols to mean any carbon chain. And so this is when we're doing generalized reactions, we might say it doesn't really matter what's over there, it's just some kind of carbon chain. And so we will put R to mean some kind of carbon chain over there, that it can vary. Sometimes in our structures we'll write an X, and that means that it can be any halogen. And a halogen, of course, would be fluorine, chlorine, bromine, or iodine. Down here in this little structure that I've written on the bottom, it's showing you how that R can work. This R, CH, double bond CH2 means there's some carbon group that is attached to a carbon, which then has a hydrogen and a double bond to it, on it, and the double bond is to another carbon with 2 hydrogens. That R group is really used a lot, so we're going to have to get used to understanding what it means. Okay, when we draw these structures, sometimes we have chains of carbons, and sometimes we have rings of carbons. If you see on the left, we have a chain of carbons, and it's called propane. We'll get into nomenclature in a little bit, so you'll understand what these names mean in a little bit. But the one on the left is a chain of carbons. The one on the right is cyclopropane, and you can see that the carbons are attached in a ring. We can draw these rings with our shorthand structure. So if you look here, we have something called cyclohexane on the left. It has 6 carbons in it. I can draw that as basically a hexagon. There are 6 corners in the hexagon representing one of each of the 6 carbons in that ring. We can figure out how many hydrogens are on each carbon, because each carbon has 2 carbons attached to it, so each carbon must have 2 hydrogens attached to it. We also will call shorthand skeletal structures, and I think your book often will call it a skeletal structure instead of shorthand. If we look at this skeletal structure, you can see that on the left we have a cyclopentanol molecule. Cyclopent means there's 5 carbons in a ring, and the anol means there's that OH on it. Well, we can draw that with our skeletal structure by just drawing a pentagon. 5 corners means 5 carbons in a ring, and then you can see that the oxygen and hydrogen are attached to a carbon on the ring. We draw in our hydrogens that are attached to any oxygens or any other heteroatoms. Even though we're not drawing them on the carbons, we do draw them on the heteroatoms, because otherwise we would get very confused. So now what I'd like you to do is try out this shorthand. And I've drawn a condensed structure, and I'd like you to draw it into shorthand. And then down below that, I've drawn some skeletal structures or shorthand, and I'd like you to count how many carbons are in each of those compounds, so that you can make sure you understand how these structures are written. In drawing the shorthand for this, I first can see that there are two carbons attached to another carbon. So I would draw the line segment going down to a carbon and then a line segment coming up to a carbon, as I have on the left there. Then that carbon that has just one hydrogen attached is right there at the intersection of those two lines that are forming something that looks like a sideways V. The other two carbons then extend from that point, the line segment being drawn slightly downward, ends on the CH2, and then the last carbon, which is a CH3, would be at the end of the line segment that is going up. In these two compounds, you can see there is a carbon that is attached to the oxygen at the top, and then a carbon attached to the oxygen that goes down. There is no carbon at the end of the line segment that is going toward the oxygen. So in the compound, as we go around, we go from the oxygen up to a carbon, then a carbon flat over to the left, then down to the point there, and that would be 3, then down to the bottom of the hexagon, and that would be 4, and then to the right would be 5, and then you're back at the oxygen. So 5 carbons in the structure on the left. If I look at this many-sided carbon ring here, you can see that there are 12 carbons altogether, because you look at the corners of each of these two lines coming together, and if you go around you can count 12 corners. So that means there's 12 carbons in this ring.